Well, here's the end of quadric surfaces. The fifth one out of six. There's 6 quadric surfaces, just like there's 4 conic sections in the plane. There's 6 quadric surfaces in 3 space. I'm going to go through these a little quicker than I would have in class because you can rewind the video if it goes too fast. This one is called the elliptic cone. This is its standard equation. Z squared equals x squared over a squared plus y squared over b squared, where a and b are numbers, right, in 3-dimensional space. We can take some traces of this one by putting x, y, or z equal to a fixed number, like z equals 0 gives 0, right, equals x squared over a squared plus y squared over b squared. Here it is. And this one's kind of tricky, right? What are the solutions to that? Well, this is not negative. This is not negative because they're both squares. So the only way to make the sum of those equal to 0 is if they're both 0. So this is only the origin, this point. That trace is a point, the origin. Within the z equals 0 plane, the only point is the origin, right, in the xy plane. We could try z equals minus 1 or z equals plus 1, either one of those planes. Either way, you put in z squared and you get 1 on the left equals all this stuff on the right, x squared over a squared plus y squared over b squared. And we recognize that's an ellipse of semi-axes a and b. So when you intersect with a horizontal plane z equals 1, you get an ellipse. Or with z equals minus 1, you get an ellipse. You can try z equals plus or minus 2. Then you've got 2 squared equals x squared over a squared plus y squared over b squared. Divide by 2. And you've got x squared over 2a squared plus y squared over 2b squared equals 1. Well, this is still x squared over a number squared plus y squared over a number squared equals 1. So it's an ellipse again, just with bigger semi-axes. Square root of 2a, whatever a was in here, and square root of 2b. So it's an ellipse square root of 2 times as big when you go up to z equals plus or minus 2. Well, you can keep this up and you can make these other cross sections, like you put x equals 0 in here. Well, then you've got z squared equals y squared over b squared. Which, if you think about it, that means z equals plus or minus y over b. But that's 2 intersecting lines of slope plus 1 over b and minus 1 over b through the origin, right? If you try and sketch this all out, same thing over here. If you put y equals 0, you get z squared equals x squared over a squared, which is again 2 intersecting lines. And see if I can move this up just a bit. What you get then is elliptical cross sections this way, intersecting lines within the yz plane of the paper and also within the xz plane here. You have an elliptic cone. Looks like an hourglass except with elliptical cross sections is what you have. Here's the z equals 1 plane, for instance. If you intersect there, you get this ellipse with semi-axes a and b, whatever the numbers were in the equation. So see how easy it is to sketch? You just recognize from seeing that equation that it's an elliptic cone, put the origin as a point, make a cross section here with semi-axes a and b, and you've got a pretty good sketch. Now let's try this one. Suppose I asked you to sketch x squared plus y equals y squared plus z squared over 4. This doesn't quite look like the standard equation. Now x squared is on the left. But it's actually the same form, just with x and z interchanged, right? It used to be that z squared was over here and x squared was over here. If you interchange the x and z axes, that just turns this thing around. So the cone now opens about the x-axis. You recognize this is a standard equation for a cone. Think of it as x squared equals y squared over 1 squared plus z squared over 4 squared. Here, let's put it here. Equals 1. And when you put x equals 1, say, to get the trace out here in this x equals 1 plane parallel to the paper, you've got 1 equals y squared plus z squared over 4. And recognize this is an ellipse in the yz plane with semi-axes 2 and 1. And so what you can do is go out to this x equals 1 plane, 1 unit out of the paper, draw an ellipse with semi-axes 2 in the z direction, 1 in the y direction. And there is one of the cross sections of the elliptic cone. And now you just draw its axis back like that, and it's like an hourglass with elliptical cross sections this way. So that's how you sketch these things. I might ask you to sketch these on the test. The book can't ask you to because it's online homework. But I can ask you to on the test. Well, here's the last one. It's the hyperbolic paraboloid, the hardest one of them all. It has this standard equation. It looks just about like some of these other equations, but z equals x squared over a squared minus y squared over b squared. If you think about it, when this was a plus, we just got the elliptic paraboloid, right? Because when you put z equals a constant, you got ellipses, x squared over a squared plus y squared over b squared. And if you put y or x equals 0, you get parabolas like this, right? Now what we've done is by changing that plus to a minus and the elliptic paraboloid, that was number 4 we did, is we've made, well, if you intersect this with the plane z equals 1 by putting 1 in the equation for z, oh, it's a hyperbola instead of an ellipse. So now it's a hyperbolic paraboloid instead of an elliptic paraboloid. And the cross section's the other way, put x equals 0, now you've got z equals minus y squared over b squared. Here it is, it's a parabola downward in the zy plane. If you put y equals 0 and look in the xz coordinate plane, you've got z squared equals x squared over a squared. That's a parabola up in the xz plane. So I have to draw parabolas up in the xz plane, here it is. Down in the yz plane of the paper, here it is. And if you think about it, 0, 0, 0 is a solution, so this goes through the origin. So I have to draw the seat of the saddle here at the origin. And then I've got hyperbolas within the xy plane. So that's what it is. Hyperbola is this way, parabola is this way, parabola is this way. It's very hard to draw. I still have trouble with it all the time, but you just think of it, you sit down on the saddle at the origin. Right? So you come down and sit down on the z-axis right at the origin, and just draw yourself a saddle, and it looks pretty good. For instance, suppose I give you z equals x squared minus 4y squared. What is this? Oh, it's this, right? Just if I write x squared over 1 squared and write 4y squared as y squared over a half squared, I recognize it's of this form, equation 2. So it's a hyperbolic paraboloid. Since z is on this side, you sit down on the saddle, right? If I put x on this side or something, I have to sit down for the x-axis is the idea. Now, here's the similar example. X on the left side. X equals y squared minus 4yz squared. Now you sit down on the x-axis and the saddle's turned this way. And you can do some specific cross-sections. Put x equals 1 in here. Get 1 equals y squared over 1 squared minus z squared over a half squared, and sketch the specific hyperbola and the specific parabolas and make this more accurate if you want. It's kind of hard though, actually. And then I want to make this very important note, even though it's not on the homework. Whenever you see an equation like this, second powers, including cross terms, x times y, y times z, and x times z, a through j are numbers, given numbers. An equation like this is always a quadric surface in 3 space, a degenerate case, or has no solutions. It's like the conic sections in the plane. Every second order equation in just x and y was either a conic section, a degenerate case, or no solution. Taking out if all the numbers are 0, then everything's a solution. Similarly here, in 3 dimensions, if the highest power is 2, including cross terms, then you can rewrite this thing in one of these 6 standard forms and sketch it. It's very beautiful, and you realize that all second order equations now boil down to being able to sketch quadric surfaces, degenerate cases, and no solutions. So it's that important. There is a little trick in here. In order to get rid of the cross terms, you have to do rotations, which we haven't done yet. But we can do it without that by completing the square. And you can see some of the degenerate cases. Like if I put a through f equal to 0, and I just get this part, what is it? ax plus by plus zz plus d equals 0, except I use different letters. It's a plane, right? So a plane is a degenerate case. And there's some other important cases too. We can get just points and so forth still. Here's an interesting case right here. The degenerate cases include what we call cylinders. Cylinders are where you take a plane curve and you extrude it. You slide each point along the plane curve in a parallel line, and so you get a whole bunch of cross sections that are all that plane curve. For instance, this one, if I wrote this equation in 3 dimensions, x squared minus z squared plus 1 equals 0, right, this is obviously the parabola in the xz plane, right, because you've got, if you rewrite it, you can write it as let's see, x squared equals z squared minus 1, right? Oh, it's not a parabola, I'm sorry. It's a hyperbola in the xz plane. you rewrite it like this. It's z squared minus x squared equals 1. It's a hyperbola in the xz plane. But this is in 3 dimensions, right? There's a y coordinate we haven't shown, so what does it look like? You draw the hyperbola in the xz plane coming out of the paper like this. Here's the branch of the hyperbola going down. Here's the branch of the hyperbola going up. You can sketch it pretty well because, right, a and b are 1 in the standard equation, and so the vertices are 1 unit up and 1 unit down along the z-axis from this equation. And you draw it nicely, right? And you can draw the asymptotes y equals plus or minus b over ax, or just the lines, or z equals plus or minus b over ax, or just the lines z equals x and z equals minus x. So here's the asymptotes in the xz plane, those red lines. And now what you do though is y is arbitrary. That means you can let y be anything. It doesn't have to be in the xz plane. You can slide it to any y coordinate. Every cross section is the same hyperbola, right? Every trace, if you will, parallel to the xz plane. Like here maybe y equals 10 or something, is the cross section, still the same hyperbola. And so what you get is a hyperbolic cylinder, right? By taking the hyperbola and sliding each point parallel, you have a hyperbolic cylinder. And this is a degenerate case too. If you think about it, this is one of the kinds of things we can get out of the equation. All right, now what we want to do is, having done cylinders and quadric surfaces in this section, be able to look at the equation and kind of tell what it looks like. Again, we'll have to rotate these things eventually to get rid of cross terms. But this is the next simplest thing after linear equations. Ax plus by plus cz equals d was always a plane of first up powers of x, y, and z. Now when we have second powers, we get these kind of things. So this is the next simplest thing. That's why they're important. They come up in all sorts of things like orbital mechanics and quantum mechanics and all sorts of other places. Suppose I just want to identify some of these equations of that form without the cross terms for now, and identify what it is. Well, what if I put x squared equals y squared plus 4z squared? What could that be? I just remember back to my equations, right? This is an elliptic cone just with x on the left instead of z, and so I sketch the hourglass coming out of the paper, and I can take cross sections of this, traces, and make a nice diagram out of that if I need. What if I see y equals x squared plus z squared? What's that? Well, I remembered before that z equals x squared over a squared plus y squared over b squared was the standard equation for the elliptic paraboloid. Cross sections were ellipses and parabolas. You could take traces and see that. If I put y on this side instead of z, then it's still an elliptic paraboloid, just opening in the y direction instead of the z direction. This is what we had opening up last time, was parabolic cross sections and elliptic cross section. So it's elliptic paraboloid opening this way, but moreover, it's something you should recognize. Think of this as x squared over 1 squared plus z squared over 1 squared elliptic paraboloid. When a and b, the things that are squared underneath here, are equal, the ellipses degenerate into circles, so this is actually a circular paraboloid that we have here. So the cross section I can draw, actually if I put in y equals 1 in here, that's a nice one. You get x squared plus z squared equals 1. Oh, it's the unit circle. So I get the unit circles at cross section. That's a nice one to draw. And then I draw parabolas this way by putting, say, x equals 0. The cross section is y equals z squared, a parabola up in the yz plane. If I put z equals 0, I got y equals x squared, a parabola up in the other plane. So here's parabolic cross sections, and circular cross sections with the unit circle in the y equals 1 plane. That was fast, and they want to rewind that one. All right, finally, what we want to do today is that finishes the quadric surfaces and degenerate cases. The next topic, and we'll just get it started today, I wanted to make sure I gave you your money's worth today, is cylindrical and spherical coordinates. One reason this section is here is that these quadric surfaces actually have very beautiful equations in these coordinate systems, and sometimes they're even simpler. Like when they have circular cross sections, like in that last example, that actually has a simpler equation in cylindrical coordinates, and not a bad equation in spherical coordinates if you turn it the right direction. All right, so here's cylindrical coordinates. These are going to be very easy, and this is all we're going to do today. The spherical will be a little harder, but still they're nice. These are for when you have a radial symmetry, and cylindrical coordinates are hardly anything more than polar coordinates add z. When you're in 3 dimensions, right, coordinates or plane coordinates, what do? You just add a z coordinate. Here it is. If you take any point in 3 space, you drop it perpendicular to the x-axis, take the line segment back to the origin, the height above or below the plane, the xy plane, gives you the z coordinates, and the same z you get in rectangular coordinates, Cartesian coordinates. But then, the distance to the origin in the xy plane from that projection is r. The angle from x towards y is theta. It's the same coordinates you had in polar coordinates. R, theta, z is now an ordered triple. We always put it in this order. And that, any ordered triple, a number for r, theta, and z, identifies a unique point in 3 space, just like r and theta identified a unique point in the plane by polar coordinates. However, the reverse isn't always true. In fact, it's not ever true. If you give me a point, there's an infinite number of ordered triple cylindrical coordinates that can represent it. Because if you give me an r theta z that represents this, I can always add 2 pi to theta and it goes to the same point. So you can add 2 pi to theta, that gives you an infinite number of points. And if you're on the z-axis, furthermore, theta can be anything. It doesn't matter what angle you turn through, you're still on the z-axis whenever r is equal to 0. So on the z-axis, theta can be anything, and at any other point you can add 2 pi to any angle theta, and it's the same point. So there's an infinite number of ways to describe each point in cylindrical coordinates, but each cylindrical triple identifies a unique point. Now there is one difference from polar coordinates. Here we require r to be non-negative. There's some problems in doing integrals and so forth. It's tricky. But you don't want that same generalization you had in polar coordinates. It causes too much trouble. So we'll say instead of r squared equals x squared plus y squared, we allow r to be negative and theta the opposite direction in polar coordinates. Remember that? We're not going to do that. Theta just has to point towards the point, and r is the non-negative distance out here. It's square root x squared plus y squared from the z-axis over to this point here. And then just like in polar coordinates, tangent theta equals y over x. You have to figure out, however, which quadrant theta is in. And z equals z, since we made it the same. So look, it's just polar coordinates add z, and it's even easier because now r can't be negative, right? Here's the other direction, right? If you take just the xy plane, here's looking down the z-axis on the xy plane. You have r, the distance coming out, and theta, this angle. You notice that x is, well, this side is, if this is r, this must be r cosine theta, so that this over this is cosine theta. And this must be r sine theta, so that this over this is sine theta. It's just trigonometry. But that means that x is r cosine theta, y is r sine theta, and z is z, just like in, these are just like polar coordinates. We're just adding z is the same number as in rectangular coordinates. Then when you go to actually solve this equation, tangent theta equals y over x, bear in mind that there's 2 possible answers, when you, 2 possible directions. Theta could be the arctangent of y over x if theta is in the first or fourth quadrants, right? The arctangent gives you an angle between plus and minus 90 degrees, plus and minus pi over 2. So if your point is over here, projecting down into the second or third quadrants, you'll get the wrong answer out of this, just like in polar coordinates. You have to add pi to put it in the right coordinate, and this doesn't necessarily put it between 0 and 2 pi. You can then adjust it if you want. But this will be a right direction. In the second and third quadrants, you take arctangent y over x plus pi. So this is saying tangent theta is this, but you have to figure out what quadrant it's in, whether you need to add pi to the arctangent or not. And these are the 2 conversion equations. From rectangular to cylindrical, you do this. From cylindrical to rectangular, you do this. Equations 3 and 4. And now we can convert points, and we can also write equations. For instance, here's an interesting case. Suppose I want to convert these cylindrical coordinates, r, theta, z, to rectangular coordinates. This is easy. 4 is just plug and chug. X equals r cosine theta. You just put it in, and you compute it. Cosine 3 pi over 4, if you go back to trigonometry, is square root 2 over 2 in this quadrant, because it's a 45, 45, 90 triangle. This is pi over 4. And you get minus 5 square root 2 over 2. Y is r sine theta. You just take the radius r5 times sine 3 pi over 4. 5 pi over 4. Should have been 3 pi over 4, but anyways, 5 square root 2 over 2 plus. And then z is just the same coordinates you had before. Pi over 4, it's not an angle, but I still use that. So here's your coordinates in r theta z, in x, y, and z, corresponding to these cylindrical coordinates. And then you can go back the other way too. And also I just wanted to point out that one of the purposes of these is when you have a radial symmetry in the xy plane, right, like you have a cylinder in a car, a piston in a car or something, then look what a simple equation you have to describe a right circular cylinder. This goes up and down forever. You can put x squared plus y squared equals 2 for a equals 2 squared for a circle of radius 2, and then z is arbitrary, so you extrude it, and it's a right circular cylinder of radius 2. But easier in cylindrical coordinates, you just put the equation r equals 2. Theta is arbitrary, so it goes around like this. You get the circle on the xy plane. Then z is arbitrary, so it slides up like this, and you get a right circular cylinder as simple as r equals 2. So that radial symmetry is taken advantage of by using cylindrical coordinates. Well, we'll convert some points the other way next time. Maybe I should just do one now, huh? Let's see. Suppose I have this. Convert the following equations. Square root 2 minus 1 rectangular coordinates. I'm sorry, square root 2 minus square root 2 minus 1, 2 cylindrical coordinates. Well, this is very easy too. You just say r immediately is the square root of x squared plus y squared. And you get, let's see, 2 plus 2 square root of 4 is 2, so r is equal to 2. And then tangent theta equals y over x is minus square root 2 over square root 2 is minus 1. Well, we know the arctangent of minus 1 is minus pi over 4. So the answer could be minus pi over 4 if it's in quadrant 4. But if the projection is in quadrant 4, but if the projection is in the opposite quadrant, quadrant 2, then you have arctangent minus 1 plus pi, which would be 3 pi over 4. Which one is it? Well, if x is positive and y is negative, then it's in quadrant 4, so you throw out this one, but you have to check it. Here's the answer, theta equals minus pi over 4. And now z is just z is minus 1, and the ordered triplet you get then is 2 minus pi over 4 minus 1, r theta z. Those are the cylindrical coordinates that correspond to these rectangular coordinates above.